Good evening, one and all. Myself, Madhuri ARADE. I'm currently pursuing PhD from MIT World Peace University, Pune, from India. And my research paper, it is based on privacy preserving ZK-SNARK based blockchain for agriculture food supply chain. My PhD research area is in privacy preserving for the blockchain. My research guide is Dr. PISE sir, NITIN PISE sir, who is working as a professor in School of Computer Engineering and Technology in MIT World Peace University, Pune. So agenda for this research paper, it is organized into different parts as introduction, then the previous literature review work, that is related work, what is the proposed work for this paper, then experiments and the results, and conclusion and the references. So as we know that in even in India or in the country, in any country, the agriculture, it is one of the foundation stone, and it is very important one uh, for survival of the human being. But to trace that originality of the food item, it is very difficult nowadays. So to tackle this problem, there is one of the solution as a blockchain based solution. So if we uh, don't know that the quality of the product, so this will be harmful for the health of the consumer also. So how can we tackle this with the help of blockchain, that is using this blockchain? We can trace it. It is one of the feature of the blockchain, traceability, transferability. So the customer, it is one of our entity, and they can check that whether this food item, it is organic one, inorganic one, that kind of verification can be done, and we get an ensurety about the originality of the product. So this is just one diagram showing the different entities are involved in any kind of food supply chain. So food supply chain means this is from starting from the farmer, how this transaction phases are completed from one entity to the another entity, that has been shown here. The first is a farmer, the farmer who produces that crop yields, and that will be transferred for its processing to the food processor. Now, what is this blockchain? Blockchain, it is the chain of the blocks. So we know that the Satoshi Nakamoto and the group of the people, they have find that started or developed this terminology as without interference of this third party, that anyone can do the transaction in the form of the Bitcoin or the Ethereum. And even these blockchain applications are also worldwide popular one, just like in a healthcare industry or the food supply chain, that we can do the smart contract, and we can trace the product. So here, when farmer it is doing the transactions, transferring that information from farmer to the food processor. In the blockchain software, it as it is a chain of the blocks, one new block will be get added, and it will be get authenticated by the consensus algorithm in the form of the smart contract. So this transaction information will include the farmer ID, the that crop yield methodology. With the help of the IoT devices, that we can store that information. And after that, this food processor will process that food item. And then again, the same repeated work will be done as of the transaction. And while transaction, smart contract will be generated. With the help of the different methodology of this consensus algorithm that we can use. For this transaction. So the distributor who is responsible for distributing this product, and the retailer will get the product items from the distributor, and the final entity will be this customer. Now customer, with the help of the barcode scanner or any of its software, that the customer will check that the food items received uh, by him from the retailer, whether it is having the originality that as per the expectation, and that will be get verified, and then customer will buy that particular item. So that is one of the benefit of the blockchain, that we can ensure that it's originality, it's a traceability. Now, in one of the point of this research paper that related work has been presented, till date, there are so many encryption algorithms has been used. Now, the problem is that the current blockchain, it is using that different encryption technology, but it is having one problem as it is not dealing with the quantum attack. That all of we know that in future there will be the quantum computers and there will be the threat that this computer will crack this encryption algorithm very easily. So these are the different algorithms and different papers are published that I have studied. These different papers included with different methodologies of this encryption, such as zero knowledge proof. It is one of it, and I have used one of it, that is a ZK-SNARK for my research paper, and ZK-SNARK is till date is a famous one. One of the zero knowledge that we don't have the knowledge of what exactly the content is, and but still we can assure that this current content is a correct one without revealing its secret. There is one identity-based encryption that works for the revealing the without revealing the identity, that data will be get encrypted. There is another methodology, famous methodology as a proxy re-encryption is also there. And some papers are, some researchers has used this proxy re-encryption for this increasing or the enhancing the security. Even the ring signature, that is just like a digital signature, that we can signature or we can authenticate the data, whatever we are transferring. Homomorphic encryption, that minute. Just we were talking about the homomorphic encryption. Let me go to the slide. So this is a homomorphic encryption where without revealing or without that decrypting the content, we are transferring the content from one entity to the another entity. And even the secure multi-party computations. So these are some implemented encryption technologies are there. And I have gone through some of the papers. But one problem with all these papers is that it can't deal with the quantum computing. So for to deal with the quantum computing, we require some another kind of algorithm. So I studied some theory for the zero knowledge proof, that is a ZK-SNARK, ZK-STARK. So the problem statement for my research is that now currently so many companies are working for this food supply chain using the blockchain based technology. That is a good thing, but there is a one problem is that it lacks the privacy. Means, for example, suppose my product is means I'm some developing some product from the that crop yield, and I'm doing some processing. I want to keep my data as my processing as a secret one. So I don't want to reveal that methodology that techniques I'm applying for processing the food items. And even at the same time, customer should get an assurance that the item that received by this customer, it is an authenticate one, and it is a originality, having the good origins. So multiple business parties are included actually in the food supply chain. And when multiple business parties are included, so every party it is interested that other that food processing business party what it is doing, and they may disclose the personal private information, and there may be some business that failure. So that is one of my problems, how that we can keep that personal private information. And secondly, that if suppose I want to deal with the quantum attack, so my system, that my software of that food supply chain should protect from the quantum threat. So both that thing should be get combined. So this is my the problem statement. So that this research will provide a blockchain-based food supply chain, and that protects the privacy by guarding against the quantum attack. Now, the next part that we will deal with, what is a zero knowledge proof, and what I have done in this research. So zero knowledge proof that we can provide the validity of the statement without revealing the statement itself, and the zero knowledge proof protocol having the three main criteria. That is, it should be the completeness, soundness, and it should be the zero knowledge. That if the input is valid, then the zero knowledge protocol always return the true. If the input is invalid, it is theoretically impossible to fool this zero knowledge protocol to return the true. And the third thing is that the verifier learn nothing about the statement beyond its validity or the falsity. So it is having the zero knowledge of that content. There are two types, major two types are there. ZK-SNARK, that is a zero knowledge second non-interactive argument of knowledge. And the second type is a ZK-STARK, that is a zero knowledge scalable transparent argument of knowledge. So in the coming slides that we will look for the ZK-STARK. So this is its name is indicating scalable one. So as we grow with our data, so that will not affect on that scalability issue. Transparent one, and having the argument of knowledge. So in the argument of knowledge, that it is using the hash function. SHA-256 algorithm is used in the form of the hash function. The main advancement over this in this ZK-STARK is that it doesn't need that trusted setup, which requires in the ZK-SNARK. So this is one of the benefit over the ZK-SNARK. So that's why I have thought to choose this one thing. And secondly is that this is one of the zero knowledge proof that is a post-quantum secure, providing the quantum security in the form of the post-quantum security. So this is my proposed work. So that entity, just we have seen the first entity will be the farmer who is producing the food items. Then through the smart contract, all its transaction will be done to the food processor, and authority will be get transferred to the food processor to the distributor to the retailer, and retailer to the customer. So for this, every transaction of the smart contract, while it is dealing, all this data will be more secure, and the privacy will be maintained with the help of this ZK-STARK protocol. So what exactly this farmer data contain? This contain the farmer ID, food item, and this quality and the quantity and the price location. Even the food processor, I mean the processor ID, the food product number, quality, quantity, and it's even the techniques are there. So what we have done, that we have chosen this two, the food processor and the distributor, as one as a sender and second one as a receiver. So one as a prover we can say, and second one as a verifier. So prover, it is a first entity that is transferring the data, and verifier, it is a verifying the data. So we have taken one use case as an Jaggery production. So in Jaggery production, that we can say that how this Jaggery is produced from the sugar cane, and there are some techniques that organic Jaggery, how it can be produced. So for that, some tricks are there, techniques are there, and that will be hidden with the help of the ZK-STARK protocol. So input items, that Jaggery serial number and the food safety result that will be provided to the ZK-STARK protocol. After ZK-STARK protocol, what it will do, it will take that input of the food processing technique and that serial number, and it will convert it into the polynomial representation. From the polynomial representation, then the prover will output a polynomial that demonstrate specific property of the food item, and it is a set. And then third, there is a test that is a FRI protocol, that is called as a fast read Solomon interactive oracle protocol. And there will be test that whether that polynomial expression, it is of the low degree or not. If it is a low degree, then it indicates that prover statement is a true one, and confirming that the Jaggery items is of the desired quality and the origin. So what do we have tried? ZK-SNARK algorithm is already present. And ZK-SNARK algorithm, it is using a library, and it is using that Lagrange polynomial interpolation for creating its input data sample into mathematical expression in the form of the Lagrange polynomial interpolation. So what was the change modification we have done? That we have used different interpolations. So we have studied some different mathematical interpolations for that. Among that, two has been chosen to compare between these three protocols, three interpolations. One is the barycentric Lagrange interpolation, fast Fourier transform, and the Lagrange polynomial interpolation. And for these three interpolations, we have seen that how it performs and which one it is a better to be used as per the time for the execution and its performance index. So this polynomial, after creating the polynomial interpolation, it includes the three steps. That is, first the creating the polynomial interpolation equations, then finding the constraint polynomial, and forming the composition polynomial. So all these are required for first to express into the polynomial form. And after finding out the composition polynomial, the prover will send this composition polynomial in the form of the Merkle tree will be get created. And this Merkle tree proof with the help of the SH256 that will be sent to the verifier. And then verifier will send some query and then check whether it is of the having the low degree or not polynomial. If it is having the low degree using the FRI protocol, then this will give output as a correct one, or the data it is a correct one. So these are the this column represent one column polynomial interpolation equation column. These are the names of the different that interpolations, and these are the formulas of the polynomial equation formula. And I got these f of x values for different interpolation. For example, I will read the one of it, that Lagrange interpolation, what I said, that it is a by default interpolation used by the ZK-SNARK protocol. So f of x is equal to minus 60x raised to 3 minus 68x minus 128. So here we have used domain size. Domain is one required for that, and domain size we have taken as a 256. So we can take in the range of the 2 raised to n power of. Barycentric Lagrange, it is using the wet component in the form of the Wj. And so this equation get changed in a barycentric interpolation polynomial. In a fast Fourier transform, it is one of the modification into the Fourier transform. It's a fast Fourier transform with this equation. And we got this value. All these value I had derived in this Python with the help of the formulas put in the Python language. Constraint polynomials, having the equation as an f of x square minus f of x. And this gives these three values for these three different interpolations. Then forming this composition polynomial, so p of x has been derived here. And for p of x, that c of x divided by u of x is that. And that is nothing but c of x that we have seen. This is a c of x divided by that 2 raised to n, that is a it's a polynomial degree will be get divided, and we got these equations for the p of x. Now this p of x, this will be used to generate the Merkle tree, and this Merkle tree will be sent to this verifier. So you can see this diagram. And in this diagram, the prover, first it is calculate the p of x, that is a composition polynomial, and even the f of x. For both, we will calculate this Merkle tree that will be sent to the verifier. Verifier will send one random number for testing whether the received data it is a correct or not. And for that algorithm generation, it is using the fast read Solomon interactive oracle proof of proximity protocol, FRI protocol. It is a by default used for your the ZK-SNARK protocol. If after certain number of steps, that is the steps will be that degree of the polynomial. So if in a certain number of steps you get that some constant value, then we can say that your data, it is a correct one. Otherwise, it is not a correct one. So in this our case, that n is equal to 4, that we have taken the 4 input values for that actually. And for the 4 input value, we are getting n minus 2, 4 minus 2, that will be the 2. So in a two number of steps, we got these, it's the correct or wrong one, and then we can predict that it is a right or it is a wrong without revealing the secret. Now, Hyperledger Composer I have used for these experiments of the blockchain. So two separate modules actually I have implemented. One is a Hyperledger Composer I learned, and uh, there I develop a supply chain. And I created all these, you can see in this left side, this diagram, picture, sorry. Participants are there. So customer, distributor, farmer, food processor, retailer. I created all these participants with some scripting behind it. JavaScript, I used the language. And here, just we have to mention add the date. And after creating the participant, there is a one transaction code is there. It is also in the form of the sample asset. In the asset, there is that code. And just you have to pass that transaction from details from one entity to the another entity. And it is supporting for the web API framework. And for this Hyperledger Composer, I installed Ubuntu app on Windows system along with the Docker, then Git, and some that Python and Node.js. So all these are the basic requirements for this installation. I implemented this as in a blockchain. That is a one separate one. And secondly, I use a Google Colab and language is a Python for ZK-SNARK algorithm. So currently I'm having the two different models. One as a Hyperledger Composer, having that blockchain supply chain, and second one as a Python, as second one as in a ZK-SNARK protocol implemented in a Google Colab. I implemented these three protocols, means the ZK-SNARK with three different interpolation just to check the result of this interpolation. So when I tested it for different parameters, that proof generation time, proof verification time, its a proof size and throughput, then I got such kind of results that if we compare these results for Lagrange, that is a by default algorithm for the ZK-SNARK. Extra two algorithms I tried, that is a barycentric Lagrange interpolation, fast Fourier transform. So when we compare the proof size is the same thing. Proof generation time for barycentric Lagrange, it is showing the larger time. Lagrange, it is quite smaller. Even the fast Fourier, it is also quite smaller. Smallest time or the very few time required by the Lagrange itself. And the proof verification type, here we can say that fast Fourier transform, it is a fast one. That its verification time is very less as compared to the others interpolation. And even the throughput, number of operations performed per seconds, if it is observed that 14.79. So 14 operations performed per second, which is more effective than barycentric and the Lagrange interpolation. I draw this graph for the first left side graph. It is showing the various interpolation performance analysis for proof generation time, proof verification time, and the proof size. So by looking at this graph, you can observe that fast Fourier transform, it is we can say better as compared to the other Lagrange and the barycentric one. Even here, so here in a various that interpolation and the throughput, if we see, then in a throughput here, the fast Fourier transform, it is having the higher throughput as compared to the Lagrange and the this one, barycentric one. So after executing implementation, so mainly the thing is that the fast Fourier transform means my plan is that in the future, I will integrate this fast Fourier transform into this blockchain along with this ZK-SNARK because it is having the better performance than the existing Lagrange interpolation. Another thing is that after integration, the future task will be that observing the performance overhead because we are adding another layer, additional layer of security over there. So of course, this will add some performance overhead. I have to work on it. Secondly, I will work on in the future off-chain which are the different formulas I have to keep down off chain, and which should be on the on chain to keep the performance at a certain level, and it should perform the better. These are the references I have gone through. Already I have mentioned all these references in the papers. Some are the research papers related to the relative work. Some are the books also I have referred. Encyclopedia, Wikipedia, I have referred for some mathematical formulas. And for Hyperledger, that Hyperledger document I have referred from the website or proper hyperledger.org for the learning the composer document, and Hyperledger also. Mm, And finally, I would like to thank you that accepting my paper, and that giving me opportunity to publish my paper in your journal.